Welcome to the ChemDoctor, and this is the second video that deals with molecular geometry. In the first video, I described how we determine the hybridization for the central atom of a particular molecule, and now what we're going to do is we're going to make the connection between hybridization, which gives us the mixing of s and p orbitals that are involved in allowing electrons to form bonds between particular atoms and a central atom. And the main thing being is that we want to now correlate hybridization with geometry. Now, one of the key fundamentals here is understanding that the hybridization of a particular molecule gives us the arrangement of electron pairs around the central atom. Technically speaking, it doesn't tell us the geometry because the geometry is based on the arrangement of atoms around the central atom. But what we can do is we can use the hybridization to infer what the geometry is. And the benefit of this is that it's a much simpler way of determining the geometry around a central atom by contrast to memorizing the tables that you find in a general chem textbook, which is the reason that I favor this method for determining the geometry of a central atom, or the geometry of external atoms around a central atom. So remember that you need to have a solid understanding of being able to draw Lewis formulas for this video, and you definitely want to have seen the first video on molecular geometry number 1 before you view this presentation. So to start with, what we're going to do is we'll look at an example that I did in the last video for carbon dioxide, and we're going to start with an example, two molecules that have sp hybridization, and we'll talk about the bond angle and the geometry. All right, so the first thing that you want to do when you're going to determine the geometry around a central atom is you need to make sure to sketch the molecule. So for CO2, its Lewis formula is going to look like this. You can see that there are two double bonds in it. All right, and I want to answer the question, all right, what's the geometry concerning this molecule? So what I'm going to do is determine the hybridization. And I do that by counting the bonding units. And around this carbon, there's literally two bonding units, one here and one here. Double bond is considered one bonding unit for the purpose of hybridization. So we have two bonding units, we subtract one, and therefore the hybridization is sp. Now, sp molecules have bond angles which are 180. So these molecules are linear. So all sp central atoms have linear geometry, and the bond angle between the external atoms is 180. Now let's look at another example here so we get some practice. All right, the next molecule I'm going to do is this one, HCN. So the Lewis formula for this one will look like this. There will be a triple bond to the nitrogen and an unshared pair of electrons here. And what we want to do, like we did in the last one, is know what the geometry is around this central atom. There are 1, 2 bonding units. So again, the hybridization here is sp. Therefore, the geometry around this carbon is linear, and the bond angle is 180. All right. Now let's go ahead and move on to the next example. And the next example is sp2. Now you'll remember in the first video what we did to look at this one was we did boron trifluoride, and boron is an atom that violates the octet rule, so it's only going to have 6 electrons around it, and the hydrogens, the fluorines will each have 8, like this. And when we go to do the hybridization, now you can see that we're going to have we're going to have 3 bonding units around this thing. All right, I'm going to change my color. I'll put a number by each one. So we've got 1, 2, 3. We subtract 1, so this is sp2. So for an sp2 hybridized molecule, these are trigonal, planar, so it's like a plate, and the bond angles are 120 degrees. All right, now let's look at another example here where we look at a more complicated molecule. So I want to look at carbon dioxide, excuse me, carbonate, the carbonate molecular ion. All right, now the Lewis formula for this is going to be like this. My writing leaves little to be desired. Sorry about the lack of beauty here. All right. And remember, from your studies of Lewis formulas, there are actually 2 more resonance structures besides this one. Well, I'm not going to get into that here. All right, so here's the Lewis formula for this. So how do we figure out the geometry of this molecule? Well, again, all right, remember a bonding unit is single bond or a double bond or a triple bond or unshared pairs of electrons. So we've got 1 bonding unit here, another one there, and another one here. So this molecule is sp2. That means it's trigonal planar and our bond angles are 120. So this is a flat molecule. It's like a triangle, you know, it's like sort of like a triangle, like this. Flat plate, all right, where the bond angles between each of the oxygens, which should be in the corner of the plywood plate, are 120 degree bond angles from each other. All right. Now, I think it's important, we should look at one more resonance structure for this, or a type of molecule. So let's really quickly do NO3 minus. So if I draw its structure, it has a similar relationship between the oxygens, like carbonate. All right, and again, to figure out our geometry, I'm going to go ahead and count bonding units. 1, 2, 3. So this is an example of another sp2 molecule. So it's trigonal planar and the bond angles are 120 around the nitrates. Now let's look at, I want to look at 2 tetrahedral examples. So that, moving down here to the next one, all right, here's where we have 4 things. So let's just quickly review. At the top, we're dealing here with the central atom that has only 2 other things bonded to it. Then we move down to the trigonal planar situations that are sp2, and notice that we only have 3 things bonded. And then down here, the tetrahedral arrangement, we have 4 things that are bonded to the central atom. This geometry here is called tetrahedral. All right, and my bond angles are going to be 109.5 on these kinds of molecules. Now, as an example, I did methane in the other one, so I think what I want to do here is we'll do CBr4, or carbon tetrabromide. All right, and its structure will look like this. Bromides will be around it. Get their electrons in here. A lot of times my students get tired of doing this, but to be correct about it, we need to get them in there. So each of the bromines have got 8 electrons around them, and then the carbon does as well. Now notice our bonding units. Let's just go through the process. We got 1, 2, 3, and 4. So this thing is sp3 hybridized, and sp3 hybridized systems where there are 4 atoms attached to the central atom are tetrahedral with bond angles 109.5. I've provided this picture here again for you to look at closely, because these top 2 molecules when we look at them on a piece of paper, it's actually fine to see them that way because those are the sort of dimensions that they have. But with a tetrahedral molecule, this representation here it's not accurate. These are not four bromines that are sitting in the plane of this paper with the carbon at the center of it. It's important for you to realize that it actually looks like this here. All right. Okay, so now let's go ahead and let's look at another example here. I want to do one that's more complicated. All right, so for this one, it's going to be SO4 minus 2. And this is going to be an example of how you apply hybridization to a molecule that has a central atom that's not following the octet rule. All right, so I'm going to go ahead and bust out its structure here. So it's going to be, this is what it's going to look like. And you can use formal charge when you do this to make sure that I'm actually correct. If you're wondering how I decided on this version of it versus some of the other possibilities, and the reason is because I used formal charges to evaluate the best arrangement of electron pairs around the sulfur. And remember, when I talk about electron pairs, you've got two kinds. You've got the bonding electrons and you have unshared pairs. All right, so let's take a look at this now. We can determine the hybridization very easily by counting the units. So here's 1 unit, 2 units, 3rd unit, 4th unit. So this molecule is it's sp3 hybridized, it's tetrahedral, bond angle is 109.5. So sulfate actually looks like this. All right, now let's look at a couple more examples here. And what I want to do is introduce 2 of the exceptions. All right, and like I said, what you're going to want to do is memorize hybridization and geometry. And there will now be 2 exceptions to this. So the first one that we're going to look at is going to be ammonia. All right, and what do I mean by exception? All right, so remember that hybridization is giving you the arrangement of electron pairs around a central atom. It doesn't give you the geometry directly. So if you look at ammonia, this is the proper Lewis formula for it. If we determine hybridization for this, it's sp3. All right, because remember that bonding units include unshared pairs of electrons. So here's 1 bonding unit, 2, 3, 4. So my hybridization is sp3. So ammonia is an example of an sp3 hybridized derivative whose geometry is not tetrahedral. All right, its electron pairs are tetrahedral. So in other words, I'm going to put that down in words. So the electron pairs are tetrahedral. All right, but the geo is not tet. Now, for these exceptions where you have nitrogen or it could be a phosphorus with an unpaired share of electrons like this, that's sp3, these are pyramidal molecules. All right, and I've provided a picture here for you to look at so you can see its shape. All right, and the bond angle is going to be 107 degrees. The bond angles between the respective atoms. All right, and the electron pair here, I'll put it in, is sitting up here on top, in the space above the nitrogen. It has the effect of compressing these bond angles down, which is the reason why the bond angle is not 109. Because remember, the electron pairs in this molecule are arranged tetrahedrally, but the geometry is based on the atoms that are attached to the central atom. Geometry is based on the atoms that are attached to the central atom. So the one thing about this is you need to be able to recognize when you're dealing with an exception, and most of the time that's going to be when you've got a nitrogen central atom, or it could be phosphorus, but there could also be other possibilities. All right, now moving down here to the next exception, it's water. All right, and if we look at its Lewis formula, we see that it also has 4 bonding units because we've got one unshared pair of electrons here, the second one, then the third, and the fourth. Two of my bonding units are two of the bonding units are a pair of electrons that are involved in bonding. Two of the bonding units are unshared pairs. So when we count them up, we got 4. So my hybridization here is sp3. So again, the hybridization here is equivalent to a tetrahedral molecule. So keep in mind what I said about ammonia. The electron pairs here are indeed tetrahedral in nature, but the oxygen is only bonded to 2 atoms, and the geometry is given by the arrangement of the atoms around the central atom. So this particular arrangement is called bent, and its bond angle will be 104.5 degrees. I'm losing it. Its bond angle will be 104.5 degrees. All right, and so almost any time you have an oxygen that's bonded to 2 other atoms, where there are 2 unshared pairs on it, it's going to have a bent arrangement. You know, and I think what I ought to do before I close this video is give you another example. So let's take a look at methanol, for example. Its Lewis formula will look like this. And I'll go ahead and extend the structure on the hydrogen, so if you're kind of a novice with the Lewis formulas, it makes more sense. All right, and then on this end, we're going to have the hydrogen coming out, and then there's going to be 2 unshared pairs of electrons. So if we want to know the hybridization now, and we want to know the geometry around the oxygen, it's going to be 1 bonding unit, 2 bonding unit, 3 bonding unit, and a 4th. So this is sp3. We recognize, though, that this is a derivative of water, so the geometry is bent around the oxygen center, and its bond angle will be approximately 104.5. It's not going to be exactly 104.5 because this methyl group over here is pretty big, and it influences the angle between the methyl group and where this hydrogen is. All right. Now I'd like to thank the watchers for viewing my presentation. I hope this helps. Remember, you can find this video on YouTube and also at my website, which is www.chemdoctor.org. And I'm going to go ahead and close now. Thanks again for watching.